This video is about terminal points and reference numbers. As always, begin by reading through the textbook and taking careful notes. This video will hopefully bring out some important highlights. We'll begin by recalling what we did in our previous lesson, which started with the introduction to special fractions of the unit circle. Now I want to review those here, so this might be a perfect time to pause the video and try to draw the full set of special fractions on a blank unit circle. And we want to get pretty good at that, so this is a good chance to practice it before I do it here. What you'll recall is that we use a circle. Now I used a clock in the introduction. We're now just using a blank, kind of boring looking plain circle, centered at the origin, unit circle radius 1. And we started, as you'll recall, counting from the right side of that circle, where on the clock, typically the number 3 is. We're starting over there in that spot as the number 0, and then counting around the circle counterclockwise, which of course is the opposite direction that clock hands typically move. Now you'll notice or recall that there are two sets of fractions that we put on the circle as our special fractions. One set is just counting by 1/6, and the other set is counting by 1/4. And then of course sometimes these fractions overlap and meet at the same place. So let me start doing that. So starting from the right side, if I count up, there are 2 sixths marks per quadrant. And so if I label those, the first one would be 1/6. If I just start counting up by sixths, then the next one would be 2/6. But instead of using 2/6, we reduced it to 1/3. So I'll use the reduced version of these. And then at the top, it'd be 3/6. Of course, 3/6 is really 1/2 reduced. And then 4/6 and 5/6. Of course, 4/6 is really 2/3. And then 5/6 can't be reduced, so we'll use that as it is. So really we're just counting by sixths in this counterclockwise direction, starting from the right side. All the way on the left side, then we would hit 6/6, which is just 1. I'll use that version. And then if we continue down the left side of this circle again in a counterclockwise direction, so we were at 6/6. We have 2 more markings, 1 per quadrant, so the bottom left zone has then 7/6, and then 8/6. Of course, 8/6 can reduce to 4/3, so we'll use the reduced version. Then 9/6 at the bottom. Of course, 9/6 reduces to 3/2. Okay, so we're still cooking around now. The bottom going counterclockwise direction. Our last little zone here in the bottom right has 2 markings. So we'll put those in place. And recall, we were at 9/6 at the bottom, which reduced to 3/2, of course. So then there would be 10/6 next, but 10/6 reduces to 5/3. We'll use that reduced version. And then 11/6 before finally making our way back up to 12/6, which is the same thing as 2. So we have 0, or you could call the same place 2, which is 12/6. All right, so these are the sixths of our special fractions, counting around the unit circle, counterclockwise direction, starting from the right side and counting up by 6. But you'll notice or recall that there was another set of fractions we have to put on the circle that are our special fractions. So we'll add those now. We also added the 1/4 places. So if you count by 1/4, starting again from 0 and going in this counterclockwise direction, then you would hit 1/4 as a place between 1/6 and 1/3, halfway between those. 1/4 is there. Then 2/4 really is the same thing as 1/2. So we'll just keep using both fractions, use that same reduced place of 1/2. That's 2/4. Moving on, we'd have 3/4, which is halfway between the markings in the upper left zone. That would be between the 2/3 and 5/6. And then we have 4/4, which is the same place as 1 on the left side. Continuing down and around, we would have 5/4 between the sixths markings in the bottom left zone. So 5/4, of course, is between 7/6 and 4/3 if we're counting around that way. Then we'd have 6/4, but 6/4 reduces to 3/2, which we already have on the bottom of our circle. Then we would have 7/4 in the middle of the lower right zone or quadrant. And then lastly, we'd have 8/4, which is the same thing as 2, already plotted back around the right side. And so this is the full set of our special fractions. It's really just counting by sixths and counting by fourths, starting from the right side, which is a little strange, but you'll see why we start there in a minute later on. And then we count our way up by sixths or by fourths, of course reducing fractions when we can, and observing that some of these overlap at the same spot. And this is the full set of our special fractions. Now this is a very important set of fractions. That's why they're called special. And what I recommend is writing this set of fractions out on a circle, just like this, probably at least once a day until you have these easily by heart, because they're that important, okay? What we're going to do today is expand and use them in a more contextualized version of them. But for now, we're just reviewing the fact that we already did put these fractions on the unit circle. Those are our special fractions. So let's also move on then and talk about a couple other things. So first of all, recall that the circumference of a circle has a formula. Now this is really back from like, I don't know, maybe geometry class or something. You might have had this, maybe algebra, I'm not sure. But this formula for the circumference of a circle has a couple different ways you could write it. You could say C equals 2 pi r, or sometimes that's summarized as pi times d. D is really just 2r. D is diameter, r is radius. So we'll just kind of note that r is radius, and if that's the case, then 2 pi r, this is our formula for the circumference of a circle. Now, since the unit circle radius, since the radius of the unit circle is 1, remember we discussed last time that it's a circle centered at the origin with radius 1, we really have that the circumference of the unit circle is 2 times pi times 1, because we're plugging in 1 for the radius, which really means it's just 2 times pi. So in other words, the circumference of our unit circle is simply 2 pi, using the standard circumference formula. Now, furthermore, all of our special fractions that we just reviewed above of the unit circle are really just endpoints for those fractional arcs. And again, this textbook uses the letter T for these arc lengths. That's may or may not be the case with other textbooks, but if we call the arcs T of the full circle, then let's label these on here. So what you'll notice now is we have again a standard unit circle, but this time I've marked on there where all the special places are. You'll notice above we had two sets. You have the sixth markings and the fourth markings. But let's notice that if you go back up and recall that all the way on the left side, we ended up with 1. Of course, those were reductions like 6, 6 or 4, 6, right? So if we notice that the left side of this circle had the result 1, and the right side was either the place we started with, which was 0, or where we ended, which was 2. And if we recall what we just did, which is that the circumference is 2 pi, that means that going all the way around the circle is really 2 pi. So we're going to call that 2 pi instead of 2. And if I mark that where all of these are special fractions of the full unit circle, then I've just put a pi with each of these. So 1 is really 1 pi, or just pi. And if I mark all the sixth places, that means I have 1/6 pi, which by the way we'll write as just pi over 6, same thing. Then remember it was 2/6 at the next 6 marking. Well, 2/6 is really the same thing as 1/3. Well, 1/3 pi is really what that is, but we'll just call that pi over 3. Okay, so what this really is all the special fractions, but now they are fractions of the full circle whose circumference is 2 pi. So if we're doing 1/6 where it's really 1/6 of pi, then it's pi over 6, and so on, right? So pi over 6, pi over 3. At the top is where we have 1/2. We'll call that pi over 2. Moving on to quadrant 2, remember we have these as quadrants. We have quadrant 1 in the upper right. We have quadrant 2 in the upper left. And those places will be as follows. So we had, counting by 6, 1/6, 2/6, which is really 1/3, 3/6, which is really 1/2, 4/6 is the next spot, but 4/6 is really 2/3. So again, if we're marking these as pi, you can call it 2/3 pi, or 2 pi over 3 is the way you might see it typically written now in trig, 2 pi over 3. Same thing, it's just 2/3 pi. That was the 4/6, and then we had 5/6, which again we'll write as 5 pi over 6. That's that lowest marking on the left upper side, quadrant 2. 6/6 pi, which is just 1 pi, or just pi. Moving around the bottom, let's finish this. We had 7/6, or in other words, 7 pi over 6. And then we would have 8/6, and the second 6 marking. Again, we're just kind of recalling all these special fractions up here. We're kind of working through this zone in the quadrant 3 area, the bottom left zone. So we had 7/6 and then 8/6, which is really the 4/3. So we'll call that 4 pi over 3. 9/6, which is really 3/2, so 3 pi over 2. 10/6, which is really 10 over 6 is really reduced to be 5 over 3, so we call that 5 pi over 3. We're now here, so we already went through quadrant 3 in the bottom left, now we're in quadrant 4 in the bottom right. 5/6, 5/3, which is really 10/6, and then we have 11/6, which we'll call 11 pi over 6. Again, all these are using or mimicking the special fractions that we wrote above, but now we're throwing in pi. Why? Because we're talking about fractions of the full unit circle whose circumference is 2 pi. 2 pi comes from the formula for circumference, right? It's all kind of built on that. Okay, now, of course, you'll know that we have more fractions to add in here. So let's not forget our fourth friends. We have all these fourth markings in between the 6, or sometimes on top of them, same ones, right? So the first one was 1/4. Well, we're going to call that pi over 4. That's 1/4 pi. 2/4, which would be same thing as 1/2, so pi over 2 at the top. Moving around, again, continuing on, 3/4, or 3 pi over 4, up in quadrant 2. 4 pi over 4, which is again just pi on the left side. And then we have 5 pi over 4 in quadrant 3 in the bottom left. 6 pi over 4, which would reduce to the same thing, 3 pi over 2 that we already have on there. 7 pi over 4 down in quadrant 4. And then all the way back up to 8 pi over 4, which is the same thing as 2 pi. So, okay, this can be a lot to take in, but if you are practiced with all the special fractions in the simple, boring, blank unit circle, which is the whole point, right? Practice that until it's easy, because then this won't be really that much more difficult. All you're doing is throwing pi in with all of these fractions. Those are all these special fractions now, but as portions or fractions of the full circle. And everything we do is pretty much built on these values. So that's why this needs to be pretty smooth. Again, not only write out the special fractions with the blank circle, but then practice using all the pi symbols as well, which is really the same thing, but now with those tossed in and all the reduced fractions. Okay, so that's how we're going to use this unit circle, but with fractions of the full circumference in terms of pi. All right, next, after getting all that in there, there's more, okay? Next, let's label what we're going to call our terminal points. terminal points, all found using our circle's equation as seen in previous lessons. Okay, so recall, the equation of our unit circle is just x squared plus y squared equals 1. There is an algebraic process you can go through with that equation to get every single one of these terminal points. Now, the details of all those computations is beyond what I think the purpose and scope is of this lesson. So I'm going to write the results on our circle here, or draw them in, and you can see them worked out a little bit in the textbook. Some of the exercises have you going through some more of them. They're just algebraic or geometric exercises using algebra to find the following points that I'm going to just summarize and put on here as our terminal point. Okay, to be clear, what I mean is this. Every one of these places on this unit circle could be marked with a point. And if you put the point on there, all of those points have coordinates, right? Like x comma y coordinates. Now, as we saw in our previous lesson, you can check whether a point is on the circle by plugging those coordinates in for x or y or both, and then making sure you get the equation equal on both sides. We did some of that. I'm going to summarize those by putting these point values kind of drawn on all of our special places. Now, there's a nice pattern to these that you will see summarized in most textbooks, and I think it's a helpful way to remember what these points are. If we start over where we started counting originally on the right side of the circle, you'll notice that the coordinates of the point over there, again with radius 1, the coordinates of that point would be 1, 0 in terms of its x, y coordinate. If you move up and around the circle at all these special places, each one of them has a set of coordinates that we could put in. Now, there's kind of a convenient way to remember them. Of course, the ones at the top, bottom, left, and right are easy. So like at the top of the coordinate plane where we find pi over 2, that coordinate would be 0, 1. The ones and negative ones are easy. All the other ones are going to be uglier looking numbers, but they're not horrible once you see this pattern. So here's the deal. As you go around the x coordinates, instead of putting the first one as 1, 0, I'm going to write it as the square root of 4 over 2. Now you may be saying, well, why write it so complicated if it's just 1? Well, because this pattern will, I think, help us. If I write it as the square root of 4 over 2, what is the square root of 4? Oh, it's 2. What is 2 over 2? Oh, it's 1. Okay, so really that is the point 1, 0. But watch this. If I do that and then continue on, all you have to do is count down from there. So the next one is square root of 3 over 2, then it's square root of 2 over 2, and then it's square root of 1 over 2. Now, the point here is to see the pattern so that you can remember these easily. We're not always going to write them this way, but this is easy to see. Notice it's 4, 3, 2, 1, and then really 0, right? So you're just kind of counting down as you go around that way, starting with the square root of 4, square root of 3, square root of 2, square root of 1, square root of 0 at the top. Okay, that pattern can help you remember them. Of course, we're going to write them in their more finished form. The square root of 4 is really 2, so 2 over 2 is really 1, okay? But you can see the pattern there. Also, the square root of 1 is really just 1, so we'll write it as just 1 instead of the square root of 1. It's easier to write that way. And then, of course, the square root of 0 over 2 is really just 0, so we'll leave that one as 0, 1 for the top. That's all the x coordinates, which kind of go in that fashion, again, through quadrant 1, going in a counterclockwise direction. Now, here's the good news. The other coordinates, the y's, just go in the opposite direction. So on the bottom right, where the point 1, 0 is, where we start, you can think of that as square root of 0 over 2, which of course is just 0. And then it counts in the opposite direction. So next would be square root of 1 over 2, which of course, square root of 1 is just 1, so 1/2. Then it's square root of 2 over 2. Then it's, can you guess it? Yep, square root of 3 over 2. And then square root of 4 over 2, which is really, again, just 1. So this way of remembering what those values are, I think is helpful. Many authors of textbooks will kind of point this out as just a convenient way to remember them. Now, here's what else is very convenient. The symmetry of the unit circle has the same symmetry of any coordinate plane. So watch this. If I know, for instance, let me get a better marking here, but if I know, for instance, that this first quarter marking in quadrant 1 had the y-coordinate of square root of 2 over 2, right? That's what its y-coordinate was. Then what do you think is the y-coordinate of the point that is directly across from it over in quadrant 3? Let's mark this one over here. It's got to be the same, right? If it's at the same elevation level, then the coordinates of that mark would be similarly the vertical, that is the y-coordinate of it, would be the same thing, square root of 2 over 2. And they would both be positive because they're at the same elevation. Now, that holds true for every single point. So again, if you look at where 5 pi over 6 is, that point has a vertical coordinate that has to match the one across from it. So let's get our symmetry marker out, our thick pink here. If I take the symmetry of that first pi over 6 point, the elevation of it is the same as the 5 pi over 6 point on the other side, on the left upper area of the quadrant 2, right? So that means their y-coordinates must match. Which means, again, let's mark this in that way, the y-coordinate there must be 1/2 to match the same y-coordinate of quadrant 1. So the symmetry there can be very helpful. Now, the same is going to hold true down below, except we can use now some vertical symmetry, right? What do you think the y-coordinate is for the markings that are on the opposite side of the x-coordinate? Well, if those were positive 1/2 above, guess what? Negative 1/2 below. And that's true for all these markings that are symmetrically aligned. Okay, so let's start marking these in quadrant 1. We have the first set of them marked with all the coordinates using the square root of 4, 3, 2, 1, or 1, 2, 3, 4, depending on which direction you're going, and then using symmetry to mark the same ones all the way around the circle. So you would expect at 11 pi over 6, way over in quadrant 4, you would expect the y value there to be the same thing, negative 1/2. Again, all we're using is symmetry here, so to mark this, right, the distance between pi over 6 and the x-axis is the same vertically as the distance between 5 pi over 6 and the x-axis. And that distance is the same on the other side of the axis, so the same thing between the x-axis and 7 pi over 6, which would be the same thing as the x-axis and 11 pi over 6. So the symmetry there is going to help us build all of these coordinates in and make them way easier to remember. Now let's get into some of the other coordinates as well. So if you'll notice where we were at pi over 6 in quadrant 1, remember that the x-coordinate of that value was square root of 3 over 2. Okay, so again, using symmetry, that's how far that point is to the right of the origin. So symmetrically, on the opposite side, so at 5 pi over 6, it's that far to the left of the origin, which means, you guessed it, negative root 3 over 2 would be the x-coordinate at 5 pi over 6. We're just using the symmetry of the circle to fill all of these in. If you know quadrant 1, you know the whole thing. Just a matter of which quadrant is positive or negative for which variable. So then we can fill in the rest. Since at pi over 4, since the x-coordinate there was root 2 over 2, then the x-coordinate at 3 pi over 4, symmetrically on the left side of the y-axis, it'll be the opposite, negative root 2 over 2. Right? Or, similarly, at 2 pi over 3, that's symmetrically opposite of pi over 3. You put those together. So that means the coordinates of that point for the x value would be negative 1/2, which is the symmetrically opposite side of the positive 1/2. And then vertically, it's the same as pi over 3, which would be root 3 over 2. Okay, so some people are more visual than others, and understandably, there's a different set of what people think about the symmetry of a circle and things. And if this comes naturally to you or seems simple, great, enjoy it. If you feel like, this looks even worse now with all those numbers on it, okay, I understand. But with some time and practice, I think you can get the symmetry down. It's probably necessary to write it out several times by hand. Maybe even mark your own, colors on it or whatever you want to draw on it to make sure you're seeing the symmetry. But we do have to be able to reproduce every bit of all this detail pretty easily, and that's kind of where we're going. This is the foundation of pretty much everything we're doing. So we have to get this unit circle down. Now let's continue on. Once you know, again, the first quadrant, you just keep symmetrically placing things in the opposite, spot. So like at 7 pi over 6 down there in quadrant 3, the x value there should be the same as the x value that's directly above it at 5 pi over 6. So that would be negative root 3 over 2. Continuing on with the symmetry at 5 pi over 4, there would be symmetry there with the value directly above it, 3 pi over 4. So that symmetry in the x direction would be negative root 2 over 2. And then the y value would be the opposite of what you saw above it for that symmetrical value, so negative root 2 over 2. Down at in quadrant 3 near the bottom at 4 pi over 3, we're going to use the symmetry from what we see directly above it. You look directly above, you see 2 pi over 3, so that point's coordinates, the x value would be the same, so negative 1/2, and the y value would be the opposite, so negative root 3 over 2. Okay, so we're getting all these points. Of course, at the bottom of the circle, that's easy, just 0, comma, negative 1. And then using symmetry around the last quadrant here, for 5 pi over 3, the symmetry there is from the pi over 3 above it. So you would expect above 5 pi over 3 it to have the exact same x coordinate, which would be 1/2. And the opposite y coordinate, because it's now flipped below the y-axis, so negative root 3 over 2. At 7 pi over 4, again, symmetrically, you're looking above it at pi over 4. And if you kind of pair those together, the x-coordinate would be the same, the y-coordinate would be the opposite. So our x-coordinate at 7 pi over 4 would be root 2 over 2. And the y-coordinate there would be the opposite of above, which is negative root 2 over 2. And lastly, for 11 pi over 6, again, we're using symmetry. We already have the y value in there as negative 1/2 from the symmetry earlier. The x value would be, well, exactly the same as it is directly above it at the pi over 6 mark. So that means root 3 over 2. Okay, so it's pretty typical to be a little overwhelmed at all the numbers on this complete unit circle, but hopefully, as you saw in the introduction of where the special fractions came from, and as you now see with the symmetry and the patterns of counting 1, 2, 3, 4, or 4, 3, 2, 1 with the roots and all that, hopefully you're starting to see that actually this unit circle isn't impossible to recreate with those patterns and draw completely on your own. In fact, that's the goal. If you can draw this complete circle on your own without looking at anything to do so, you are well on your way with everything we're going to need for a lot of stuff in this entire class. So the class is more than this circle, but of course it's kind of all based on it, which is why this is incredibly useful at this point. All these points, now that have their coordinates, are called the terminal points. And again, where did all these numbers come from? Well, the algebra behind that, or the geometry behind that, is beyond what I find useful to put in this video. It's demonstrated in the textbook, and even some of the exercises have you working through it. It's just kind of some regular algebra 2 kind of stuff, or intermediate algebra. But I'm not going to walk through all those details here. I think it's more time than it's worth. So what I'll say lastly here, like I said already, is notice the symmetry of the circle, because this will help you remember it. And if you use the symmetry, all you really have to know is how to count with fractions by either sixths or quarters, and you really have to memorize the coordinates of one quadrant of this circle, and you can just kind of map those across symmetrically to get all the other ones. So thankfully that's all helpful in trying to memorize everything in this circle. All right, now moving on to our next definition, we're going to say this: the reference number the reference number, now it's denoted with a T and a bar over it in some textbooks, maybe not all textbooks, but you might see like a lowercase letter T with just a line over it. You could call it T bar, and it's associated with T as the shortest distance along the unit circle between the terminal point determined by T and the x-axis. Okay, what in the world does that mean? Well, we'll write out and draw out an example of it, but I want to make sure this notation is clear. So you'll see this written sometimes, T bar or T with a line over it. That's referring to the reference number. Some books might call it a reference arc, but it's the same kind of thing, a reference number. Now let's see an example of this with some now familiar looking numbers. For example, observe the reference numbers for T equals 5 pi over 6, which we know is one of our special places, and T equals negative 2 pi over 3, which is somewhat one of our special places. The negative's a little strange or new to us, but 2 pi over 3 looks familiar, right? So we're going to work with these to try to find the reference numbers for each. It's probably helpful to start with all of our standard markings, so you'll kind of get in the habit of this eventually. You want to put your, each quadrant has like its 3 markings. If you go back and look at all our special fractions, they end up using either the actual top, bottom, left, right, or any of these 3 markings per quadrant. So I'm just going to kind of sketch those in here so we get a little frame of what's going on. Our first one to work with is this T equals 5 pi over 6. So let's start by recalling where that is on the unit circle. If you go back to your basic collection of special fractions, 5 pi over 6 is in quadrant 2, so the upper left zone, and it's the lowest marking to the x-axis. Now, let's note that that is the place of 5 pi over 6 if I were starting from 0 on the right side of the unit circle, right? So 5 pi over 6, if I started at 0 and counted counterclockwise, or kind of stretched out my arc all the way around the circle counterclockwise and ended at 5 pi over 6, that's what we're talking about. Now, the reference arc, or the reference number, is a bit different. It says, basically, what's the shortest distance between where that terminal point is and the x-axis. So the reference number for our first arc would be to say wherever you are at this terminal point down to the x-axis, just straight down to it. So for that one, we would say T bar, our reference number, is how far is that distance? Well, that's the same distance as it would be from 0 to the first marking, right? That's just pi over 6. So our reference number for T equals 5 pi over 6 is pi over 6. Let's take the other value now. So we have T equals negative 2 pi over 3. Now, that's a little new to us. So this negative value that we're seeing in front of there simply means we're going to go the opposite direction. So if you look at our unit circle, we typically start on the right side at 1, 0, where 3 o'clock was, right? And we usually go counterclockwise to count in a positive direction. When you're working with a negative value for an arc length, then you're going in the opposite direction, which is actually clockwise. So the question is, if I'm going now clockwise, how far do I go to go 2 pi over 3? Well, really that's just a special fraction of 2/3, right? Or 2 pi over 3 is like the 2/3 mark. And it's going in this opposite direction, which is actually clockwise. We got to now kind of count backwards though. So 1/3 would be at the first marking. Normally we find pi over 3 in quadrant 1. Well, if you go in the opposite direction, then negative pi over 3 is in quadrant 4. Normally 2 pi over 3, 2/3, is in quadrant 2. Well, this time negative 2/3, or negative 2 pi over 3, is going to be in quadrant 3, in the bottom left zone. So actually, if I'm trying to go from 0 to negative 2 pi over 3, I go clockwise all the way down to negative 2 pi over 3, which is going to be the same place, by the way, as 4 pi over 3. If you look back at our unit circle, you'll notice that's normally 4 pi over 3 down there in quadrant 3. It's the same place as negative 2 pi over 3 because you're going negative 2/3, just in the opposite direction, same amount of distance. Okay, so that's the arc we're working with. We want to find the reference arc for it, which is the distance, the shortest distance from where that point is to the x-axis. Well, if you wanted to run home to the x-axis, wouldn't you go to the left of that reference point because it's shorter? You're closer if you go continuing on clockwise. So for that one, we will say, let's see, let's get a different color here. We're going to go continuing on in that direction from the terminal point in quadrant 3 for negative 2 pi over 3. That distance is really just a third of a pi, or it's a special fraction of 3. So we would say this, t bar reference number is going to be just pi over 3, meaning that's the reference number for original value of negative 2 pi over 3. Okay, so again, this all builds on the symmetry of the unit circle, which is why really that's foundational. If you still feel like you're struggling to understand what these fractions mean, where they come from, I'd go back and keep on working through this unit circle to get to the point where you can draw the whole thing without any help or looking at any examples of it. If you can do that, this will be a lot easier, all of this reference number and everything else we're going to do with it. But these are just some examples of defining and then using some reference numbers called t-bar, denoted with t and the bar over it. Okay, let's do some more work with these. Same kinds of applications here. For these next examples, we want to find the terminal point, that is p comma xy, on the unit circle determined by the given value for t. Okay, so this time they're just giving us a t value. We don't have to worry about the reference number, although it may come in handy, as you'll see. And we'll just work through each one of these. In every case, we're going to be looking back at our original set of special fractions above, the one we did completely with all the coordinates on it and all the pi values. This is just picking out whichever one of those applies. So in example A, we have t equal to 3 pi over 2. So the question is, where is that? Well, again, if you start all the way on the right side and you go 3 pi over 2, you may recall, that's all the way around where we are at the bottom of the circle. That's what 3 pi over 2 means. They want us to find the terminal point there. Well, the coordinates of that point, the x comma y coordinates, is all coming directly from our crazy circle above, right? The coordinates of that point are just 0, negative 1. X value is 0, y value is negative 1. So that's it. That's all we want to do for each one of these. For part B, this time they're giving us t equals 7 pi over 6. So again, we got to remember where that is on the unit circle. 7 pi over 6, you could say that's, if you're counting by sixth, that's 1/6 more than 1, right? 6, 6, 7, 6. So you may recall that's in quadrant 3. We'll go all the way around to 1 pi is the first half of the circle, and then the first mark after it is the first sixth counting. So that would be 7/6 if you're drawing that on there. And of course, we want a terminal point for that. Again, refer back to what our symmetry is. 7 pi over 6 here had the coordinates negative root 3 over 2, comma, negative 1/2. So those are the coordinates that we're working with here. Negative root 3 over 2, comma, negative 1/2. And again, with practice, all of those symmetrical points can get easier, and they will. It just takes a lot of practice. All right, let's keep going through these in the same kind of way. The next example for C here gives us t equals 5 pi over 3. Okay, so again, we've got to remember where 5 pi over 3 is. 4 pi over 3, so you can count up or refer back to the circle. If you draw it out yourself and you still feel like you need it kind of with you to do these kinds of problems, that's okay. In fact, it's okay to use the complete unit circle that you draw out at the beginning of a test, for example. So you can do a brain dump to put it all on there, draw the whole thing, and then use it. You've already produced it yourself, so you can use it for things on a test. That's fair. You may want to practice doing that, that's fine. So 5 pi over 3, you'll recall if you have your full unit circle drawn, 5 pi over 3 is in quadrant 4, the lower right zone. It's the first marking down there. So 5 pi over 3 is going to be, if we start at 0 all the way around to quadrant 4, it's the first marking you hit if going counterclockwise around the circle. That's 5 pi over 3. Of course, it has a coordinate point, and that's what we're looking for here. Notice the x value is going to be positive there. The y value is going to be negative. And so this is going to be a 1/2, comma, negative root 3 over 2, coming from our point values listed above. Okay, and then part D, lastly, this one is negative pi over 2. Well, again, what we saw above earlier is the same thing here. Negative just means you're going in the clockwise direction. It's the opposite of what we've been doing, okay? And for that direction, pi over 2, that's a quarter of a circle. So that would take us down to the bottom of our circle. That's 1/4 of it. Of course, the coordinates there are simple. It's 0, comma, negative 1. Okay, so in these examples, really we were just finding the terminal point, the x, comma, y coordinates of where the arc stops. And that's what we've now demonstrated with these. Moving on, number 2 says find the reference number. So now we're back to this t-bar thing for each value of t and the terminal point determined by it. So now we're kind of doing both. Okay, our first one for part A gives us t equals negative 2 pi over 3. Well, again, negative just means we're going in a clockwise direction. We got to think about where 2/3 would be. So 1/3 would be, if we're kind of moving down the clockwise direction, 1/3 would be the same place. Let's see, if you go back up to the original, you can see we're going the opposite direction. So it'd be like the second of those 6th marks, or you could say at the last bottom mark in the quadrant 4, that's where negative 1/3 would be. So negative 2/3 would be another one of those, which means it would be all the way over to quadrant 3. So negative 2/3 means you're going in a clockwise direction from the point 1, 0, all the way down 2/3, basically, right? We're counting by thirds here, or you could, again, count that as 4/6 if you want to count all the 6 marks. And that's the place where it is. Of course, there is a coordinate there. We want to find the reference number for those. Remember, the reference number is the shortest distance from that place to the x-axis, which would be continuing on. And that t-bar value would be, well, that's 1/3 of a pi. So it'd be pi over 3. That distance is 1/3, right? Think of it 1/3, 2/3, 3/3 to make up the whole pi at the bottom half there. So pi over 3 is it for the reference value. That's t-bar. And then the terminal point as well, the point where that original arc stops. So that, we could say, is the point. Of course, the x value is negative, so negative 1/2, comma, the y value is also negative, so negative root 3 over 2. Again, referring to all of our values we have above in the complete circle here. So again, if we can redraw those easily, and we can count with fractions in either direction, that's all we're doing on these. Now, the last example is a little bit different. This one has a pretty large improper fraction. So now t is 17 pi over 4. Well, 17 pi over 4 was not on our original unit circle. You will not find that number on there. The biggest it goes is, well, 11 pi over 6, and then it goes up to 12 pi over 6, which is 2, right? But that's the biggest it goes. 17 pi over 4, where we are in this one, is not even on that list. So what in the world do we do with this? Well, we can simply try to rewrite it or reorient it. So 17/4 is an improper fraction, which means you could convert it into a mixed number. And it's actually easier to go this way. So turns out 17 divided by 4 is really just 4 and 1/4. You could do that on a calculator. 17 over 4 would be 4.25, right? Or you can do long division if you want and get a mixed number. You get a remainder, and that gives you the 1 over 4. So since 17/4 is really 4 and 1/4, 17 pi over 4 is really 4 and 1/4 pi. And that will help us know how to map this out. So if it's more than 2 pi, which it is, you're going to go around the circle more than one full time. Remember, one full revolution is 2 pi from our circumference above. So if I start, I'm going to kind of spiral this one just to give it more visual aid here. If I start, again, we're supposed to be starting from the point 1, 0. But if I move in a little bit just so you can see it, if I go around the circle a half, the top half, that's pi. If I go around completely, that's 2 pi. If I went all the way around again, another half, that's 3 pi. If I go around completely twice, that's 4 pi. We're almost there. We just got to go another quarter, which would take us up to the same spot we are with a quarter pi. So it's a little bit crazy, but sometimes spiraling it can give you a good visual aid. And I'm going to do it again so you can see how this goes. You got to just count it very carefully. So it's 4 1/4. Here's a little bit quicker. So here's 1, 2 pi, 3 pi, 4 pi, and then a quarter more. And that's where we stop for our resting place. So that's our full arc. Now we want the reference number. Okay, so let's put that in. The reference number would be, again, the distance between the x-axis and where we stopped. The shortest way to go is just right back to the point 1, 0. And that distance, since we're at the quarter marks, that's just pi over 4. So we'd say t bar equals pi over 4. And the terminal point there would be root 2 over 2, comma, root 2 over 2. Again, see above for our full circle for that.